So there is a way, we call it a clever reaction, of synthesizing carboxylic acids using Grignard reagents. So if you notice in this reaction, we have Grignard reagent and we have carbon dioxide. But carbon dioxide is not, in this case, the gaseous phase, but it's dry ice, so it's solid. So if you mix these together, react them, you will produce a carboxylic acid. But let's see the mechanism. So you know that this is nucleophilic, carbon is electrophilic. So the attack will occur at the carbonyl carbon, and then you will add CH3, CH2. So notice what is being added. So we form a carboxylate. Now, once again, make sure you understand what's being added. So this is this right there, the ethyl. All right, so then the next step would be to add an acid to protonate this. The reason why you're using an acid, it's because this is weakly basic, so it needs a strong acid to react with it, and you end up with carboxylic acid. Very well. So let's go to the next part here. It says summarizing Grignard reagents, organolithium reagents, and cuprates. So far we studied that Grignard reagents and organolithium compounds are extremely strong bases and powerful nucleophiles that add to type 1 and type 2 carbonyls and epoxides. So we may have haven't covered epoxides, but we will, at least when we meet, because they produce really useful reactions. So remember, epoxides are these. Because they are strong bases, you can't make Grignard or organolithium reagents from compounds that contain acidic hydrogens. We already talked about how it will react with itself and stop the reaction. And since organocopper reagents are made from organolithium reagents, they also can't be made from compounds that contain acidic hydrogens. Again, it reinforces the statement that was made earlier. So here are, again, you can't use any of these acidic groups on the Grignard reagent. By the way, this is an alkyne. So once again, just an important reminder, we cannot make a Grignard organolithium or organocopper reaction from compounds that contain these groups. Because Grignard reagents react with carbonyls and epoxides, that also means you can't make Grignard reagents from compounds that contain epoxides and carbonyls. The same holds true for organolithium reagents and cuprates. So here are the possible Grignard reagents. We have an alkyl group, an alkyl these are methyl. This is an isopropyl. We have a benzene phenyl group with a methoxide attached to it, etc. We have an alkene, and a tert-butyl. So all of these are possible. So let's give you an example of something that is not possible. Not possible. So once again, we already talked about this one. This will react with itself. Even if you have something like this. So, or an epoxide. So these will react with themselves. So let's look at the second one here. So if I were to draw another one of these, instead of this adding to, let's say, something else, and if I just draw another one right here, this will react with another Grignard reagent. It could, of course, as well not produce again the desired product. And again, that's not allowed. But if you look here, you do not have, it can't react with itself. There isn't a carbonyl, there isn't an acidic proton, there isn't an epoxide that it can react with itself. So again, make sure you remember that part, that again, no carbonyls, no epoxides, and no acidic protons or any of these acidic groups. Very well. Grignard reagents and organolithium reagents do not react with alkyl halides in an SN2 reaction. So that's just a quick mention. So we would think this is an SN2 reaction like this, but the reaction actually doesn't take place. So we're expecting this to happen. Okay, but this reaction does not take place. So make sure you are aware that the reaction does not take place. Very well. Cuprates have their own unusual chemistry. They react with epoxides and acid chlorides, but they do not add to other types of type 1 or type 2 carbonyls, as we mentioned. They also add to alpha, beta, unsaturated carbonyl compounds in the beta position exclusively, and we'll see this later in the semester. So I'll probably show you an example in the next few on the next few pages, but we'll examine it later in the semester in chapter 24. So let's look at cuprates here, how they react with epoxides. So what you need to remember from epoxides, maybe if you haven't seen them before, is that we have an electronegative oxygen atom. So that's delta minus. And that's delta plus. So we have an electrophilic carbon. So I'm going to erase this because I need to draw an arrow and show you. So again, you know, R2CuLi, tack, and open up the ring. And what do you think water is going to do? It's going to protonate this oxygen. So the end result would be something like this. So we'll just show the intermediate here. Okay, if you're having a hard time understanding how we added this, just pay attention to this. You have 1, 2, 3 carbons. Let's say this is 4 and that's 5. So it's 1, 2, 3, 4, and 5. So we now protonate and we end up with an alcohol. So once again, building up our arsenal of reactions so we can make an alcohol from an epoxide organocopper reagents. Now, when nucleophiles that undergo irreversible carbonyl additions are used, the carbonyl addition is observed. Okay, so these are statements that we're making now because we will study them more in depth, especially in part 2. Okay, so this is the addition. We've been talking about this, where we have the carbonyl addition product. You end up with, let's say, an alcohol, and you have an R group here, an R group, and an R group. That's the addition product. Or if it was sodium borohydride, if you recall, lithium aluminum hydride, etc. Or, of course, you can have with sodium borohydride, you know, it has its certain reactions with ketones and aldehydes. So when nucleophiles that undergo reversible carbonyl additions are used, the conjugate addition product is observed. So we're going to delay this, right, to chapters 22, 23, and 24. We will see those more in depth. I didn't want to introduce them right now because, again, they could they could be too much with lack of depth here. So what I want you to know from the next 2 reactions is simply the outcome. I'm not asking for mechanisms. So we already talked about this lithium aluminum hydride because this has to do with the alpha beta. And here's what we mean by the alpha beta. Alpha is the first carbon in the alkene and beta is the second carbon. Okay, so the difference between lithium and aluminum hydride and the organocopper, let's say in this case, is that the attacks occur at different carbons. So with the lithium aluminum hydride, it's going to attack at the carbonyl carbon. But with the organocopper, the attack will happen at the beta carbon. Now, once again, I just need you to know the outcome of this. So the outcome of this is you have an OH and we added, this is the CH3, and of course we have the H. We've already gone over this reaction multiple times. Now, as far as the second reaction, the outcome is the following. Okay. So let's number some. So we can say this is the beta. This is the alpha. And then there was a methyl added. There was a methyl added. There's a methyl. So this is the methyl. All right. So basically the attack is the following way. You have, just to show you a, and then it undergoes a series of reactions here where you end up with still the carbonyl, but you added a carbon at the end. So always when you have something like that, you're attaching one more carbon, not to the carbonyl, but to the last carbon, in the double bond, which is the beta carbon.